Alright, section 7.4 is all about similar triangles, and we're going to talk about different ways we can prove triangles are similar based on their sides being proportionate or the included angle and their sides. Okay, so for the first one, we have side, 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 and this compares three corresponding sides and seeing if they are proportional, if they reduce to the same ratio. So in this picture here, I'm comparing the side AB right there with the side PQ, and I'm setting a proportion, so I'm setting it equal to the other set of corresponding sides. BC would correspond to QR, so that's wrong. Let's fix that. Let's fix that in your notes. And then CA would correspond to RP or PR right there. Okay, so if these are all true, if all those sides, when I put them in a fraction form or creating a proportion, if they reduce to the same ratio, then I have a congruent triangle. And here's how I would write that congruent statement, right? I would have to go in a specific order. So if I choose to go A, then B, then C, I would do the same thing over here, P, then Q, then R. So this is how I would write that congruent statement, okay? Another way I could prove triangles are similar to each other is by the side angle side theorem. So first I would need an angle to be congruent, so angle A and angle P in this case, and then the two sides that are next to that angle. So I would go BA right there and compare that to QP right there, and then set that equal to the other side that's like hugging that angle. In this case, that's CA, and then this would be RP or PR, okay? And then if these two sides reduce to the same ratio and that included angle is congruent, then I can assume that these two triangles are going to be similar. They're not congruent to each other. One's clearly bigger than the other, but I can at least set up a proportion to help me solve for a missing side. Okay? Now the last part is the corresponding parts of similar triangles. If I have two triangles and they are similar to each other, then each pair of corresponding angles is congruent and each pair of corresponding lengths is proportional. So two things here. If I have similar triangles, then the angles can be congruent to each other. The only thing that can be congruent but instead is proportional are the lengths. Okay, so in this case, even though one triangle is smaller and one triangle is bigger, their corresponding angles can be congruent. These can be the same, SY, and then T and Z. They can both be the same number of degrees, but then the sides are just going to reduce to the same ratio. So they're not going to be, one side's going to be shorter than the other, for example, but they will reduce to the same ratio. And we'll we'll work through how to do that in the calculator here in a moment. All right, so let's jump into some examples. For the first one, or the first two, we want to know if the triangles are similar. If so, write a similarity statement and then explain our reasoning. So looking at this first one, I'm going to be comparing the sides and figuring out if they reduce to the same ratio. And here's what I mean by that, okay? I'm going to compare 9 and 6. Now, it's important that when you are setting these up, if you want to go big triangle on top and then little triangle at the bottom, you stay consistent when you're setting up your proportions, okay? So in this case, I'm going to go 9 over 6, and I'm going to compare it to the next bigger side. So if I'm looking at my big triangle, the next big side is 7.5. And then my next big side in the little triangle is going to be 5. Okay. And then setting that to my next big side in the big triangle would be 6. And that is going to be compared to 4. Okay, so when I go ahead and put these in the calculator, so you're just going to enter 9 divided by 6 here. That should give you 1.5. And when you put 7.5 divided by 5, that should give you 1.5. and 6 divided by 4 should also give you 1.5. So this is what we mean by they reduce to the same ratio, okay? So they all reduce down to 1.5. So we can assume that yes, these triangles are going to be similar. And then I have to write down my congruence, or similarity, sorry, not congruence, similarity statement. So if I start off with, let's say I go A, B, C, and then the one squiggly means similar, which is different from congruent. Congruent is an equal sign and then the squiggly. This means congruent. We are not talking about congruent triangles in this section. We are talking about similar triangles. So that's one squiggly only. Okay, so if I went ABC, now I gotta go DEC. Okay, and that would be my congruence, or sorry, I keep saying that, a similarity statement for this one. Similarity. Okay. The second triangle, I'm going to do the same thing. So I'm going to be comparing the sides again. If you want to go big triangle on top, little triangle at the bottom, you can do that. So big triangle, I'm going to start off with the longest side. I have 12.4. And I'm going to compare that to the longest side in the other one, which is 11.1. And I'm going to see how that compares with the other lengths. So then I have 8.2 in my big triangle. And I'm comparing that to 7.1. And lastly, I have 6.6. And I am comparing that to 5.5. Okay, so when I put these in the calculator, when I put 12.4 over 11.1, I get 1.17. When I do 8.2 over 7.1, I get, I think it's 1.15. And then for this one, I get 1.2. Or maybe it's 1.25. Anyway, we're trying to get you to see that these are not going to be the same ratio. They do not reduce to the same ratio. And by you showing that they don't reduce down to the same decimal, you're showing us that's how you know that these are not going to be similar to each other, okay? So that's all you have to do is put it in the calculator and see if it works or not. All right, let's go on to the next example. Determine whether triangle DEF with vertices DE and F is similar to L and M. Explain your reasoning. So let's start off by graphing this. I have D at -4, 0. Then E at 6, -1. And F at 3, 3. So that's my first triangle. Then I have L at -3, -5, which is down here. 15, -7. So we're going to have to extend our graph a little bit. And we're going to estimate about there. And then 11, -1. And that's N. So there's my new triangle. So I'm trying to see if their sides reduce to the same ratio, okay? So two ways I could do this here. I could find the distance formula, or use the distance formula to find the distance of all parts of this triangle and then compare if they're the same. Or because I have the graph here, I can actually also compare their slopes. So let's look at their slopes here. They should have the same slope. The slope and the distance formula are related to each other. And if they are, then they would be similar, okay? So here I have rise 1, 2, 3, run 1, 2, 3, 4, 5, 6, 7. So 3/7. And then for the side that would be corresponding to the green one, I would be LM. So my rise here would be 1, 2, 3, 4. And run is 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14. So 4 over 14. If I were to reduce this one, this would reduce to 2/7, which is not equal to 3/7. And we can do that a few more times to compare the slopes, just to be sure. But they're going to not be similar to each other. So I can compare this one and this one, look at those slopes, and then same thing with DE and LM. So in this case, you can just say no, and because the ratios are not the same. Okay. All right. Then sometimes we'll give you a picture like this where we have a triangle within a bigger triangle and decide if we have two triangles that are similar to each other. So here is a little triangle, and we are going to need some help looking at the bigger picture here. So we're going to compare the little triangle within to the bigger triangle on the outside and see if the sides are similar. They reduce to the same ratio. Okay, so I'm going to start with the little one, the blue one, and I'm going to set it up as the left side, so 10, over the right side, 12. And I'm going to see, does that reduce to the same thing as the left side of my big triangle? So here's the tricky part. You have to figure out what the left side is. The left side in this case is 15 plus 10, which is 25. And then on the right side, 12 plus 18, which is 30. So then here, again, the 10 was the left over the right. So I'm going to compare that to the left, which is 25, over the right, which is 30. So see if these reduce to the same thing, okay? 10 over 12 reduces to 5/6, and so does 25 and 30 reduce to 5/6. So yes, we can say that these are similar. I'm going to do it one other way so that you can see that you can actually do these multiple ways. You can also do left over left and see if the right over right reduce to the same thing. So if I'm looking at the left of the little one, that's 10, over the left of the big one, that's 25. And then the right of the big one is 12, over the right of the weird one is 30. These would reduce to 2/5 and 2/5. So they have the same reduction. You just have to keep it consistent on which two sides of the triangle you're comparing, okay? Whether it's left over right or left, left, right, right. Either way, if they reduce to the same thing, then you can assume these are similar. So for, I need two things. I need yes, and I need a similarity statement with the one squiggly. Remember, that's what similar means. So in this case, if I want to go N, M, P, so I'm going up and then down, then I'm going to say R, M, S. So again, start down, go up, and then back down. So that's how I came up with my similarity statement for this one. Okay, and lastly, I have a word problem. So we have somebody that wants to measure the building. He stands so that the tip of his shadow coincides with the tip of the building shadow. So we have a person here, and he is 5 feet 6 inches tall. Okay, and his shadow is here 18 feet. At the same time as the shadow of the building happens to be 360 feet. So we're looking for X. Okay, we have to figure out how big the building is, and we have to set up a proportion here. So look at the information that you know. We know more information about the little triangle, okay? So I'm going to say that we're going to compare 5.5 to 18, and the 5.5 represents the height, and the 18 represents the shadow. And the first one, we're talking about the person, okay? Then we're going to set it equal to, and the building. The building, we want to know the height of the building. The height is on top, but we know the shadow of the building, and that's 360 feet. So before you begin cross multiplying and doing all that fun stuff, it's important that for these word problems, you make sure that you have the same units. So like if one was yards and feet, we would have to convert them all to the same unit. So be careful with that. And then that you set up your proportion. Again, in this case, I want the height to be in the numerator and my shadows to be in the denominator before I go through. So now that we set up a proportion, this is just cross multiplication. So I'm going to grab my calculator and I'm going to cross multiply 5.5 times 360 gives me 1,980. And then 18 times x, I'm just going to write as 18x. Then I'm going to divide both sides by 18. And that gives me 110, which is x. So then go back and make sure you're answering the question. This means that the building is 110 feet tall. Okay, and that would be your final answer.